Okay, so for our introduction to exponential functions and logarithms, we're first going to review our exponent rules that we started in the fall. It'll be really important to have these dialed in for success in this unit. So if this continues to be a problem, seek me out and we can do additional practice. So for our first rule, we have our product rule, which is what happens when we multiply two monomials with the same base together. And you can see this here, x and x have a same base, and I've got x to the m times x to the n. What happens when I multiply two bases that are the same? Two bases that are the same, I add the exponents. So you can see here in this example, this becomes x to the m plus n. In our first example here, we have x to the third times x to the 8. This becomes x to the 3 plus 8, or x to the 11th. And I'm using the caret here because I can't seem to get the superscript to work for my exponent. So this caret just means that it's x to the 11th. In example B, we have 2 to the 4th times 2 to the 2nd. And even though we don't have a variable here like x or y, these 2's are the same. They're matching. So they have the same base, so I add their exponents. So it becomes 2 to the 4th plus 2, so it would become 2 to the 6th. Here I have two variables within this monomial. So I have x squared times y, and then I have this multiplied by x cubed times x to the 4th, or y to the 4th. And the way that I'm going to do this is I'm going to isolate my terms. So I'm going to isolate my terms here. So I have x, let's see if I can get this to be in a particular color. So I have x here and x here. So I'm going to isolate that x squared and x cubed, so it becomes x to the 2 plus 3. And then I have y to the 1st power here times y to the 4th power here. So it becomes y to the 1 plus 4. So I'm just combining like terms here and adding them with the same bases involved. So x to the 2 plus 3 gives me x to the 5th, and then this is times y to the 5th, so it would just look like x to the 5th, y to the 5th as my answer. So this would be my answer here, would be this one. So for my quotient rule, this is when I divide. Quotient is what I get when I divide two things. I can be dividing numbers like 28 divided by 7. My quotient would be 4. Or I can divide monomials, and when their bases are the same, I keep the base, so x and x. So I keep my base of x and I subtract the exponents. So here in this example, you can see I have x to the m over x to the n, and it becomes x to the m minus n. So here I have x to the 5th divided by x squared, so that becomes x to the 5th minus 2. X to the 5 minus 2 becomes x to the 3rd. Here, even though I don't have a variable, my bases are the same as 3, so I keep the 3. And I have 5 minus 3, so it becomes 3 to the 2nd, or 3 squared. In C, I have two variables here, so I have to isolate like terms. So I have my x's here. So I do those first. X to the 2nd over x to the 1st is the same as x to the 2 minus 1, because remember, this x here is an exponent of 1. And then I multiply that by my y's, so I have y to the 5th divided by y to the 3rd, or y to the 5 minus 3, so it becomes x to the 1st times y squared, or I can rewrite that as xy squared, like that. In my zero exponent rule, any base except for 0 when raised to a power of 0 equals 1. So this can be like 325 to the 0 power equals 1. But here we're going to use variables just to show what I mean by this. So with this first example, I have x to the 0 times x to the 8th. And you could use your product rule here. X to the 0 plus 8 would just be x to the 8th, or you could recognize that this is equal to 1, and I could do 1 times x to the 8th, which just equals x to the 8th. Same thing for this next example. I could distribute this 0 inside, and I'd have x to the 0, y to the 0, or 1 times 1, or I could just say this whole thing is raised to a 0 power, so that's 1 times y, or y. So in this case, anything raised to a 0 power except for 0, any base except for 0, is going to be equal to 1. In my power rule, when I raise a power to another power, I keep the base and I multiply the exponents. So for this one, in this example, I have x to the m to the n, and this becomes x to the m times n. So in our first example A here, we have x to the -2 to the -4th, and instead of dealing with all those negative exponent properties, we can just multiply -2 times 4, and we can get a positive x to the 8th here. So we don't have to deal with any reciprocals or anything like that. And again here, we're used to rational exponents now from earlier this unit, but because we're raising this to another power, I can just simply multiply here, and it cancels out that rational exponent and makes it a whole number, which makes it a lot easier to work with. So this just becomes 3 to the 1/2 times 4, which is the same thing as 3 squared. With my expanded power rule, this is simply just telling me that I have to distribute an exponent that is on the outside of my monomial, or anything really. I have to distribute it if it's outside the parentheses. So this gets a lot of you when we have a binomial, or if I have an addition or a subtraction in here, because sometimes you're tempted just to distribute the exponent. But when I have an addition or a subtraction in here, I have to FOIL. But with this, because I'm multiplying these two together, I can just distribute this exponent through, and I can get x times y to the m is the same as x to the m times y to the m. Same thing if I have a fraction here, I can distribute this exponent to both terms, and it becomes x to the m over y to the m. So in this first example A, I have 2a to the third, and this would become 2 to the third times a to the third, which I can simplify as 8a to the third. In example B, this is 6 squared times, and here I also am using my power rule here, so it becomes 6 squared times x to the 6, or I can rewrite this as 36 x to the 6. And for these up here, I can simplify these. I forgot to do that. So 3 squared equals 9. If you went through and did these already, that's great. Here again, 3 squared equals 9. 2 to the 6th power is 2 times 64, I believe. So if you went through and did those already, good for you. And then we have our expanded power rule with some fractions. So in this first one, I have x to the 8th power. So this is 2 to the 4th power. And I'm dividing that by y to the 4th power. So I distribute this fourth power to both terms here. And then do this just to make it easier to read. And then here in this, I have to make sure I distribute this third power to every term, so not just to my variables, but also to my constants. So it becomes 2 to the third power times x to the third power. I'm going to put both of these in parentheses, like this. And then I divided by 3 to the third power times y to the sixth power. And I can simplify this as 2 to the third power equals 8x cubed divided by 27, 8x cubed divided by 27y to the sixth. And because I couldn't simplify 2 divided by 3 here, and because my x and y terms were as simple as I could get in the parentheses here, I know that this is going to be as simple as an answer as I can get. This is going to be my simplified answer. All right, so to finish off our exponent rules, we're left with negative exponents, which, if you all remember from the fall, it means that I have to create a reciprocal and then do the exponent value in either the denominator or the numerator, depending on where this negative exponent occurs. What we didn't really look at too much, but most of you caught when we were doing our rational exponent exercise earlier this unit, was that if I have a fraction raised to a negative exponent, I can just reverse the fraction or flip the fraction on the inside and make the exponent positive on the outside, which is pretty awesome and makes this a lot simpler to deal with instead of doing like a fraction over a fraction and then simplifying that way. So if a factor in the numerator or denominator is moved across the fraction bar, the sign of the exponent is changed. That's just a different way of saying what I just told you in terms of flipping the numerator and the denominator and then changing the exponent sign. So for our first example, we have 3 to the negative 2, which does not equal negative 9. That is not what you should get for that answer, and it's really clear to see how that can happen, but this is where memory and practice really is important here. So when I have a negative exponent, the first thing I need to do is I need to take the reciprocal. So this would be 1 over in this case. So 1 over 3 to the second power. So 1 over 3 to the second power equals, let's get this all in one line here. So 1 over 3 to the second power is the same as 1 over 3 squared, which is 1 over 9 would be my answer for that one. For B, x to the negative first power does not equal negative x. Instead, it equals 1 over x. And for this next one, let's apply this new description of this rule here. I can first flip my fraction 2 over 5, and then I can change the sign of my exponent to be to the third power, 2 over 5 to the third power. I'm going to use my expanded power rule from up here. So it becomes 2 to the third divided by 5 to the third, and that becomes 8 over 125 would be my answer for that. So that makes this a lot easier, and if you wanted to check your answer, you would do 5 to the negative 3, which would be equal to 1 over 125, or 1 over 5 to the third power, and 2 to the negative 3, which is 1 over 8, or 1 over 2 to the third power, and 1 over 125 divided by 1 over 8 would give me 8 over 125 when I divide my fractions. So now what we're going to do is we're going to do this exponent practice. I'm going to have you do just the evens for homework, and that should be all.